All right, ladies and gentlemen, today we are going to be talking about population dynamics. At the bottom there we have our target for today. So the target for this set of notes will be how are population densities affected by birth, death, immigration, and immigration. So those direct factors that would affect a population. And we'll be looking at the densities of population today in our notes. So first question I want you to write in your notes is, what is a population? Okay, so back to our set of notes here. So first question I want you to write down is, what is a population? We're gonna talk about that. We already have the definition in our article, but just to have that one more time in the notes is going to be a good thing for you guys to have. So what is a population? So when we look at a population, what we're looking at is a population is a group of the same species that occupy the same geographical area. Okay, so when we look at this picture, we see these gazelle, and that would be one population. But there's actually many different populations in the same area if we were to look at it in more detail. We have the grass, and we may have insects in the grass, but those would all be different populations. So any population of the same species, and to be the same species, they need to be able to breed with one another. So next question I want you to write in your notes, what changes how many individuals are in an area? So what is going to change those numbers, the numbers of individuals? And that's one of the most important things we're going to talk about this week, is what can change those individuals in that population in a given area. And we have talked about this a little bit in the past, but when we talk about this, the things that can change those given populations, we're looking at those direct factors. So when organisms in that population die, or when new organisms are born, okay, that population is going to grow, or vice versa, it's going to decrease that population when organisms die. Now, kind of along those same lines, we also have populations that are going to be affected by immigration, which would mean coming into an area. So organisms from a different population may be moving in. And then immigration, which is the opposite, where those organisms in that population would leave. So they would leave to maybe go to a different population. So if it's immigrating, we're going to see that population going up. If we have organisms immigrating, that population will decrease. So in your notes, just to make a double check, you should know what a population is by now. You should also have those direct factors. So this is going back to target 1. What can directly change the number of individuals in that population? And that would be birth rate, death rate, immigration, and immigration. So that would be target 1. So next question, this kind of goes back to our original target for the day. What is population density? So take a second, write down what you think population density is. But when we're talking about population density, or write down this question in your question side. When we look at population density, when we look at the density of something, we're looking at the number of individuals per unit area or volume. So we're looking at the number of individuals that occupy a certain area. So when we look at population, we're looking at individuals of the same species in a given area. When we look at the density of that population, now we're looking at the number per unit area. So we're looking at how many are actually there. And so if there's more individuals in that area, the density would go up. As looking at this picture, the population density is really high for the species of birds along the shoreline. If we were to see less in this picture, if they're more spread out, we would say that population density is lower. Okay? So population dispersion, which is another one of our targets this week, and it was talked about in the article, is how individuals in that population or in that area are spaced out. So how they are dispersed. Okay, so we find 3 major patterns when we look at population dispersion in those populations. One of those is what we call, well, I'll give you a second to write this down, but one of those is actually called clumped. And so we see that here in this picture. And I want you to make sure that you write down these 2 questions. So what type of dispersion pattern is this? This would be a clumped dispersion pattern. If you look at those fish, we have groups of them kind of spaced throughout that area. So they're in nice little clumps. Now, the next question, this is a blue level question. So, I want you to write down, predict what the benefit of this pattern would be. Now, this is one of our target questions as well in that same target. So when we look at clumps, and we look at these fish, we got to think about why they would group themselves this way. And one of the main reasons we see clumped, which is the most common dispersion pattern in nature, one of the main reasons we see this is for protection, especially for those prey organisms, the ones that get fed upon. They're going to be able to protect themselves. But maybe you can think of maybe one more. So in your targets, make sure you have why. Why do we see this in nature? Another one, and there it is, so clumped. Another type of pattern that we see in nature is going to be represented by these penguins here in this picture. And you can see by the little diagram there, they're kind of evenly spaced. So make sure we write down this question. So what type of pattern would this be? And then what may cause this pattern? So this pattern would be uniform. Okay, and the reason why we see this would be a lot of times due to territory. So these penguins have their own territories, and these are probably males, and the males actually in this species will incubate the eggs. So they have their own territory. They don't want any other males coming into that area and messing with their unborn offspring. So they have their own specific territory, their own bubble, so to speak. Okay, so uniform. One of the main reasons why we see this pattern in nature is because of territorial needs. Okay. Another one here, so this is the last of the three. This was also talked about in the article, and when we look at this one, we are looking at random. So when we look at plants, a lot of times we will see this dispersion pattern represented by plants because of where their seeds will land and where they'll eventually germinate and grow. So when we look at this particular plant, it's kind of a nice example. When we look at dandelions, we can see how their seeds spread in just a random pattern. So not really a pattern at all. But anyway, so that's random. And the reason why is because of those windblown seeds. So that's a good example of why. And again, that's one more thing you need to have in that target when you answer it. Okay? All right, so in your notes, again, at this point, you should know what population density is. We talked about the number of individuals in a given area. You should know what the dispersion patterns would be. What is population dispersion? The way that they are spaced out in the area that they occupy. And then you should also know what the three patterns are and also why we see them. So three patterns would be clumped, random, and uniform. All right, when we talk about growth patterns, when we look at population growth patterns, one of the things that that you need to know about is when we talk about population growth is going to increase under ideal conditions. Ideal conditions could include, unlimited food supply. It could include the lack of predators, water quality, all those things, those limiting factors that maybe aren't as present in a given area. That population would increase under ideal conditions, and what we call that type of population growth is exponential. And so your question is, first, how do we graphically represent that type of growth under ideal conditions? Okay? So if we think about that bread and we see that mold growing on there, okay, pretty ideal conditions for that population to grow and expand. So if we were to think about that population of the mold, how would we represent that population graphically? And the way we would do it is what we call a J-shaped curve, okay, where we see that unchecked, unlimited growth, okay, and we call that exponential growth. So it's a J shape. If you look at our graph, we have population size on the y-axis, and then we have time on the x-axis, and you can see as time goes on, because they have unlimited resources and unchecked growth, it's going to increase. The rule of 70 kind of goes with this, with your exponential growth. So when we look at the rule of 70, we have this 70, which is our number, divided by the growth rate. So if we look at the percentage, you're going to divide that by your growth rate percentage. So if you're looking at a growth rate percentage of 25% per hour, okay, in 280 hours, it will double. Okay, so it's the rule of 70 for exponential growth. Okay, so it's 70 divided by the percentage growth, in your given time period that you want. Okay. Logistical growth, we look at logistical growth on the other hand. If we look at the beginning part of that graph, we're going to see an increase in the population, but at some point it's going to level off and it's going to be represented by an S-shaped curve. Okay, so if we look at that second question, what is the difference from exponential? Okay, it's going to level off, right? At some point, we're going to see that population, instead of continuing to increase and increase and increase, it's going to level off. So the third part of this slide, make sure that you write down 3 predictions as to why you think this population of fur seals may have started to level off around 1935. Okay, so if we can think of 3 reasons why, I want you to write those down. Think about why there would be a leveling off of this fur seal population. Okay, and when we look at logistical growth, one thing that we can see from the graph like this is we can predict what's called the carrying capacity. Okay, so carrying capacity is the number of individuals that can be supported by a given area. Okay, so if we look at this fur seal population, we can predict where the K value is, or our carrying capacity is, on the graph by noticing where it starts to level off or stabilize. Okay, and it's shown on the graph there as K. It looks like in the thousands, we're looking just over 11,000 individuals that can be supported by that area. So again, to predict carrying capacity, which is another one of your targets, you need to be able to see that stabilization of that population, and where that starts to happen is what we call the carrying capacity. Okay, and the carrying capacity is determined by those limiting factors in the area. Okay, whether it be temperature, water quality, food availability, predators in the area, all those things contribute to creating that carrying capacity for a given population. Okay, this last one, we're just going to watch a quick video about human population growth, and then I want you to list 3 limiting factors that could apply to human population growth. Okay?
A thousand years ago, there were only a third of a billion people, but we were multiplying. Now there's 7 billion of us. How did we grow so much, so fast? Say this glass is North America. The fuller the glass gets, the more people there are. Water drips in as people are born. Water drips out as people die. Okay, here's the entire world. Now let's go back 1,000 years. The Americas are nearly empty. Europe and Africa have less than 100 million people between them. And just like today, most people live in China, India, and the rest of Asia. For centuries, things stayed pretty much the same. Births are canceled out by deaths. Women are having lots of babies, but most babies die before they grow up and have families of their own. We don't reach 1 billion until 1804. But things are changing. Better medicine and better agriculture are starting to slow the leak from the bottom of the glass. People still die, of course. But more babies grow up and have babies of their own. Lots of babies. We've grown from 1 billion to 7 billion, and it only took 200 years. Will we keep going like this? Probably not. The UN says we'll level out at 10 billion by the end of the century. So as we continue to grow from 7 billion, the question is, can the world hold that many people? Experts can't agree. It all depends on how well we manage our food, water, and energy.
Okay, so make sure that you have listed those 3 limiting factors that you noticed in the video. Maybe you can think of a couple more. So limiting factors that would apply to our human population on Earth. Okay? All right, so when we look at this definition here. So it says to identify the vocab word associated with this definition. And the definition right there is in quotes, dramatic fluctuations with remarkable regularity. So when we look at the word fluctuations, we're looking at changes in that population. So, and we're looking at dramatic changes. So a big rise maybe, and then a big fall. So if we were to figure out or try and think about what vocab term that would go with, the one that makes the most sense would be what we call our boom and bust. Okay? So a boom and bust cycle would show populations that go way high and then they drop significantly. So we see this boom when they rise and then bust when they drop down. We look at these boom and bust cycles. What we're usually looking at in these representations is what we call a predator-prey relationship, where we see the prey population increase, and shortly after, because there's new prey available, we're going to see that predator whose main food item is that prey, the snowshoe hare in this case, its population is going to increase shortly after. Then as that prey population starts to decrease, following that, the predator population will then decrease as well. So in this graph here to the right, you can see what's going on. You can see the snowshoe hare population dramatically increasing, especially when there's not a lot of lynx around. Then as that population increases, we see the lynx population increase. As that snowshoe hare population decreases, so too does the lynx following suit. So we've seen this. This has been studied, and by this fur company back from 1850 to the late mid-1900s, and we can see dramatic fluctuations with remarkable regularity. Okay, so it matches that description. Okay, if we were to look at this population graph, okay, this is human population. So make a prediction as to what type of population this would be out of the boom and bust, your logistic or exponential. And maybe you have to see, but the population is over to the right, and you can kind of see how it increases. And that is in the billions. Okay? And if we were to look at this, more than likely, if you didn't get exponential, okay, human population is growing at an exponential rate. Okay, and we just watched a video earlier on that. But think about reasons why we have been able to continue to grow in this rate. Okay, so Germany. So this is a population graph of Germany. If we were to look at this, which type of population growth or population trend would we use? And that would be logistics. So you can see where it starts to level off, and we can actually predict the carrying capacity based on this graph for Germany. Okay, should be around 82 to 83 million people, or 82.5 million, somewhere around there, or 82. Okay, but that's going to be your carrying capacity, is where it starts to stabilize. So in your notes at this point, you should know what exponential growth looks like. How is it shown graphically? What logistical growth looks like? How it is shown graphically? What a carrying capacity is, you should know that, and then what causes a boom and bust cycle. Okay. The last couple of things we want to talk about are limiting factors. Limiting factors affect how large a specific population can grow in an area. The carrying capacity is limiting factors contribute to that carrying capacity. We have two types of limiting factors that we've talked about in class. We have biotic, which means living, and then abiotic, which would mean non-living. Okay? And when we look at an ecosystem, just to kind of show how we put this together, an ecosystem is going to be a community and its abiotic environment. So all the organisms that live in that area, plus the abiotic factors, which could include, like in this picture, maybe the quality of that water, the temperature that we see on a daily basis, the weather, the climate, all those things contribute to an ecosystem. So we include the abiotic environment when we talk about an ecosystem. If we're talking about a population and community, we don't include those factors. And then what are some limiting factors for a given population? Okay, we've kind of talked about this a little bit in class already, but just to kind of go over that one more time, if we look at an ecosystem, what are going to be some limiting factors for different populations that would be found in those ecosystems? And so if we were to list some, predators would be one, so predation. That would be a biotic limiting factor. Competition is a big one. Another biotic limiting factor, competition with other organisms or competition within that population. Disease, Okay, so different pathogens that can cause disease would be limiting factors for a population. Okay, so that's 3 biotic. Now we're going to go into abiotic. So I want you to give me an example of an abiotic limiting factor. And here are 3. So 1 would be climate. Okay, so temperature or weather over a long period of time in a given area. And then biotic could be food supply. Okay, and just to make sure we know this, environments and resources are finite. At some point, certain resources that maybe were in abundance could start to run out, and so we will have these become limiting factors to the populations that live there. And when we talk about that, this tension, this balance of those resources, of those limiting factors, is what we see in that given ecosystem. And it affects the abundance of species in a given ecosystem. Again, when we look at an ecosystem, one thing that allows us, or what tells us whether or not it's healthy or not, is the amount of species that live there. If we have a high biodiversity, that's a good indication that that ecosystem is doing well and that it's healthy. If we have less organisms living there, that's usually an indication that the ecosystem might be struggling a bit. And if we think of Yellowstone, before the wolves, we saw less biodiversity than after they were introduced. So again, here's this last little check of what you should have in your notes. You should know the difference between abiotic and biotic. You should know what a limiting factor is. And then you should know some examples of biotic and abiotic limiting factors. Okay, that's the end of the notes. Make sure you write extra questions, do your repetitions, and write a summary. Thank you.